Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 79, word search. Given an m by n grid of characters board and a string word, return true if the word exists in the grid. The word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter cell may not be used more than once. For example, if we're given this board here, and we're given the word A, B, C, C, E, D, what should we return? Well, we can see that we can find the word because we can go from A to B to C to C, E, and D. So how exactly do you solve this problem? Because it's really easy to look at our board here and figure out that we can do it, but obviously we need to write an algorithm. Well, we do have some hints. What we know is that, well, we can't use the same letter more than once, so that's going to help us. And we know that words need to be adjacent cells, right? And here, adjacent is actually defined as 4 directionally, not so much 8 directionally. So we can only actually go in 4 directions. Even though the problem doesn't tell us that, we can't go diagonally. So what we need to do is we need to see if the current tile we're at, we're going to parse through our matrix here, and we're going to look for tile values. And if the current tile value equals to, the start of the word that we're looking at, so we have an A and an A, which means that now we have, we can start our search from this tile here. And what we need to do is now we need to find B, C, C, E, D in the, tiles that are connected to this A. So we can try going up, but obviously that's outside of the grid, so that's not going to lead anywhere. We can try going left. Obviously that's not going to go anywhere, so we can't go there. We can go to this S, but obviously S is now not equal to this B, so that way we can't go here. But we can go to B, and that's a valid move, because now the word that we're searching for, we've already found the A, so now we're looking for B, C, C, E, D. So now we're at this B. And from this B, we're going to, follow the same thing. So now we found A and B. Now we're looking for C, C, E, D. So we can go 4 directionally. So we can try going up, we can try going down, and here's where we have to be careful. Because if we go left, well, we will be revisiting a cell that we've already used, right? So we cannot use the same cell. So we need some way of marking whether or not we've actually used a cell, because we don't want to be going back to cells that are already been used. So in this case, what we're actually going to do is once we take a cell as part of our path, we're actually going to mark it with just some, non-English character, a hash sign. And, I'm going to use a hash here. And what we're going to do is use that to basically indicate that we've already visited that cell. So for this B, we would mark this as a hash. So from here, we can essentially go to C, and then from C, right, obviously this is the next character, so now we found this C. And now we need to look for C, E, D. So obviously we now go here. Obviously that's not equal to the C that we're looking for. We can go up, which is not equal to the C we're looking for. We can go left, but we've already been here, so we don't actually go there. Then we go to this C. So now we found it. Then we set this equal to a hash. And then we continue the search, and we're going to keep doing this until we either find our word or we don't find our word. Now let's say our word here was actually, Q at the end. So, we would search, we would get to this D, and then we realize there's actually no, Q's anywhere. So what now needs to happen is, what we need to do is we need to go back the way we came. So we can think of this as a sort of like backtracking algorithm. So when we find a word, when we find a tile which works as the start of our, word here, so this A, what we're going to do is we're going to kick off a depth first search to basically try all the possible paths we can find, and in hopes of finding, a word that equals to this, A, B, C, C, E, D. Hopefully, we can find it. But what's going to happen is if we don't find it, remember that we were setting these hashes each time. So what we need to do is on our way back up the recursive stack, we actually need to reset those values back down to whatever they were originally, because we can't consider them explored anymore now that we've, gone through the entire recursive stack. So we need to reset them back to what they were. So we're going to have to keep track of what the original one was. So that way, when the recursion ends in all 4 directions, we can reset our character here in the case that we need to continue. And our algorithm is essentially going to be, if we kind of just get rid of all of this drawing here is we're going to have a depth first search function, which is looking for, whether or not the tile that we're moving to is going to be equal to the first character in the word that we're searching with. And we're going to go from left to right through our matrix in hopes of finding it. So we're going to start at this A here, and essentially we're going to say, okay, does our current tile equal to the word that we're searching for? The first character. Yes, it does. So that means that we need to kick off the search in 4 directions. So now we move, to the B, and then obviously we've already found the A. So then we're looking for, this C, and that's how we're going to go through it. So essentially what we're doing is we're kicking off a 4-directional depth first search from every tile that we can start from. And then we're going to perform that, recursively down until our word is either, an empty string, which means that we found all the possible characters, because we're going to chop off the first character each time when we find that character. Or what we're going to do is we're not going to be able to find our word, and we simply need to undo the recursion and then reset, any hashes that we set back to the original character. And then what we're going to do is we're going to continue through our iteration. So we'd go to the B, the C, the E, and obviously this one's a bit weird because you can actually solve it from the first tile you visit, but essentially you would have to go through until you can find it, unless you can't find one. Although I think this problem, you will actually, no. If it's not in here, you just return false. So that may not make a whole lot of sense, but I think once you see the code, it'll be a lot clearer because it's quite simple. It's another one of these matrix problems where we're doing some sort of like traversal through it. This time it's going to be a depth first search. We have to explore all possible combinations and directions in hopes of finding our word. Obviously, this isn't one where you can use a breadth first search. So let's go into the code editor and write this out, and hopefully it should become a lot clearer than perhaps this explanation has been. I'll see you there. We're back in the code editor, and it's time to write out the solution for this problem. So remember that we want to go from left to right for each row and essentially try our search at each tile that starts with the same letter as the word that we're searching for. And we're going to kick off our 4-directional depth first search until either we can't find any of the word that we're looking for, or we find it, in which case we want to return true, and we will be done with this problem. So let's set that up. So we're going to say for row in range, len board, and then for column in range, len board 0. What we're going to do is we're going to say if board of row call equals to word 0. So essentially if our current tile equals to the start of our word, then that means that we can kick off our word search from that tile. If not, we just continue. And so when we're at this point, then we can call into our search function, and if that returns true, that means that we were able to find our word. If not, then we just continue. So we're going to say if self.dfs, and we'll define this function in a second, and we'll pass in the board, we'll pass in the row, and we'll pass in the column. If this function returns true, then that means that we were able to find our word, and we know that we're done. Otherwise, we just continue through our board, and either we're going to find the word or we're not going to find the word. So if we ever break out of this double for loop, then we can simply return false because we know that the word does not exist in the board. Okay, so that's the exist function written, but this is the simple part. The DFS function is going to be the more complex one. So let's define it now. We'll say def DFS, and remember this is going to take the board, it's going to take the row, and it's going to take the column, right? And actually it's also going to take the word, apologies. Word, let's pass that in here because obviously we need to search for the word. So remember that each time that we find, a character that the word starts with, we're going to chop that, and then we're going to look for the remaining string. So what that means is that if we make enough chops, we'll eventually end up with an empty string, right? Because if we're just looking for D, we find it, and then we chop the D, then we will just have, an empty string here. So in the case that we end up with an empty string, we know that we found our entire word, and we can return true because that indicates that we found the word that we're searching for. So we can say if not word, we can simply return true. Otherwise, we need to perform the search. Before we do that, we need to make sure that the actual position that we're at is a valid position. And what do I mean by this? Well, say we're at this A, right? Our options are to go in 4 directions. We could go up, left, down, or right. But if we go left or up, we'll notice that we'll be outside of the grid. And if we try to access that index, we'll get an index error, and our function will blow up, and we won't actually solve this problem. So we need to make sure that we're actually at a valid position and we're not violating the bounds of our board. We also need to make sure that the tile that we're moving to actually has the word that we're searching for. Sorry, the character that we're searching for, right? Once we found the A, we know that we're looking for the word BCCED. There's no point of going to the tile S because obviously S is not the next character we're looking for. We only want to move to a tile that starts with a B. Otherwise, there's no point, right? We wouldn't be finding A, B, C, C, E, D if we went to AS, right? It just doesn't work that way. So that's another thing we have to make sure that we check for. The tile that we're moving to is actually going to have the next character that we're looking for. And remember when I said we want to make sure that we don't reuse characters more than once, right? The problem tells us that the same letter cell can't be used more than once. So what this means is that once we visit a cell and we take it as part of our path, we need to mark it with some sort of non-character value to indicate that we've been there. So we'll choose a non-character value. For my solution, I'm just going to use a pound sign or a hash, whatever you want to call it. We're going to use that to indicate that we've been there. So if we reach a tile that has that value, then we know that, hey, actually this is not a valid tile because we've already taken it as part of our path. So those are the 4 things we need to check before exploring whether or not we can go from this current row and column position. So let's write that out. So we're going to say if 0 less than or equal to row less than len grid. So this is checking whether or not the row position is valid. And we're going to check whether or not the column position is valid. So col less than len grid. And actually this should be board. I don't know why I call it grid here. So board. And what we want to check is, okay, we need to make sure that we're at a position that is not already been visited. And remember that I'm going to use a hash sign to indicate that it's been visited. So we need to make sure that it's not a hash sign. And we want to make sure that the actual tile that we're at is equal to the character that we're looking for. If not, then there's no point of us continuing the search. So board row col actually equals to word 0. So once all those conditions are met, then we can continue with our search. Now remember that I said we need to mark our grid to actually indicate that we've been to a tile. So what we're going to do is we need to overwrite our board at the current row and column index to indicate that we've been there. But before we do that, we need to be careful, because if we mark it and we don't reset it, then subsequent depth first search will actually have that tile marked, which won't be true. If we kick off a depth first search from this A position, let's say, and we go down a path and it turns out we can't find it, we need to make sure that we undo any modifications of our board, because when we search from the next position, we don't want that to be affected if it's not part of that original DFS that got kicked off from A. Say we couldn't find it here, we need to make sure that if we kick it off from B, we don't have those tiles marked, because that would be incorrect. We only want the tiles marked as part of an individual search. So that way, when our depth first search recursion bubbles up back to the original invocation here, along the way, we need to undo the setting of a current tile to hash if we encountered it. So what we need to do is we need a placeholder value for that original value so we can reset it back when we bubble up the recursion. So we're going to say board of row column. So this is going to hold the current position, and now we can overwrite it safely. And I just want to mention that this solution does assume that you can actually overwrite the board. If your interviewer tells you, hey, I don't want you doing this, then what you're going to need to do is maintain a visited set and use that to check whether or not you've been somewhere before by maintaining tuple pairs of rows and columns to indicate whether or not you've been somewhere. Again, you're going to have to undo the visited set, so you're going to have to pop elements as you bubble up the recursion to make sure that subsequent DFSs from a different starting position don't have that state of the visited in them. So we are going to set this equal to a hash. Now what we need to do is explore all the 4 directions. So we're going to say for row increment, column increment in, let's see, in, and then what are all the 4 directions that we can go in? So we can go 0, 1, we can go 0, -1, we can go 1, 0, we can go -1, 0. So those are our 4 directions. And we want to say if self.dfs, so we're going to pass the board, we're going to pass in the row plus whatever that new row movement is going to be, plus, the column plus the column increment, and then the word. So now that we've found this character at the beginning of the word, we now need to chop it out. So we're going to say word starting from 1 onwards. So if this DFS returns true, then that means that, again, we were able to find the word, similar to how we have it here. Then we can simply return true. Otherwise, if we can't find it in any of those 4 directions, then what we need to do is reset our board to basically whatever that placeholder value was, to undo the fact that we set it to this hash, because we don't want subsequent DFSs to be affected. And then all we need to do is simply return false. And that's going to be our function here. So let's submit this and make sure that it works. And it should take a while to run because it is quite a large grid and it's a depth first search, so we try all possible things. So hopefully this works. And okay, cool, it does. So what is the time and space complexity here? So the time complexity is, in the worst case, we're gonna have to go through the entire grid, and only at this last position here are we gonna kick off a search which is successful. So because of that, it's gonna take, big O of n time to reach that last tile, right? And we can think of n equals to rows times columns, right? Because that's the dimensions of our matrix. So that's gonna take n time to reach this last tile here. And then within that, we have a depth first search. So what is the complexity of our depth first search? Well, each time, in the worst case, we can kick off a search in 3 directions. And why is it really 3 directions? Because even though there's 4 directions we can travel, one of them will always be the place that we came from. So technically, we're not actually searching in that direction, because remember, we have a check here to make sure that we don't go searching down a path that we've already been. So technically, there's only 3 paths that we can really search from any given position in the worst case. So what this means is that it's actually going to be 3 to the L complexity for our depth first search, where L is going to be equal to length of word, right? So we have 3 options, and we're going to have to do that search however many times our length of our word is, right? So that's going to be your time complexity. And as you can see, this is an exponential solution, so that's why it took so long to run. And then the space complexity here is actually going to be big O of n, because we're only performing 1 depth first search at a time. So in the worst case that our word is the entire grid, then our recursion stack is actually just going to be holding the entire grid, right? We would have to go from like A to B to C to E to S to C to F to S to A to D to E to E. So basically it would just be holding the entire grid. So our space is going to be big O of n. So that's how you solve this problem. It's another one of these like weird matrix problems where you're basically going in 4 directions, searching. This time it's actually a depth first search. A lot of the times you do breadth first searches in these, but typically, yeah, it's not too difficult once you know how to set this up and how to basically check for the boundaries and then some condition that needs to be met for your search to continue. Anyway, if you enjoyed this video, please leave a like, comment, subscribe. If there's any videos you'd like me to make, please leave them in the comment section below and I'll get back to you. Otherwise, thanks for watching. Have a nice day and bye.